So let's actually look at one of these machines. And you'll think, okay, Ryan, this is super easy. Why are we even looking at this? So we got to start somewhere. We got to start at the most basic level possible, okay? So let's look at a two-state machine. Not billions of states, just two simple states, and that's it. So here's the machine that we're going to look at. And I'll explain all of the notation in gory detail in a second. And there is our humble machine, machine numero uno. Okay, so what in the world is this machine? The circles here, so all of the circles, so Q0 and Q1, ignore the outer circle on Q1 for now. Just the circles, those are states. So each one of these, so these are states of the machine. So is Q0 a state? Yes, because it's encased in a circle. Is Q1 a state? Yes. So, okay, so that's fine. What are these arrow things between the states? So what are these arrow things? These are transitions. And then you may say, my watch thought I saw said, hey, Siri, okay? So it recorded everything I just said and tried to make a search off of that. All right. So you may think, okay, these transitions, I see one between Q0 and Q1. It has a certain label on it. And the other direction, it also has a label on it. You mentioned, Ryan, before that the transitions between the states on a computer correspond to executing an instruction, right? And I'm pretty sure, but I think 0 is not an instruction of a computer. Is 0 an instruction of a computer? A real instruction that you would run on your x86 processor. Is 0 an instruction? I mean, a bunch of zeros might be, but just a single 0. No. So what is the beauty of this class again? Abstracting the details. I don't care what the instruction is. I just simply don't care. If I see a 0 on the input, I'm going to execute that transition. So if I'm in the state Q0 at any point, and I see a 0 on the input, what state am I going to go to? Q1. If I'm in state Q1 and I see a 0 on the input, what state am I going to go to? Q0. I know it sounds tedious, but it's important. Okay? Does everyone understand the transitions between the states? I'll get to the other stuff in a second. Yeah?
Would it be incorrect to call the transitions input since it goes from one to another, or is that something?
You can call them inputs, yeah. I'm going to use the term transitions. So sometimes I'll use on input 0 from state Q0, we go to state Q1. Okay? So, but you can think of inputs, transitions, exactly the same. Because each of the transitions has a single character label on it. Any other questions about the transitions? So, what do you think this arrow is that's coming from nowhere going into Q0? What do you think that represents? The start state, right. So we gotta start in some state. And because computers are deterministic, we can't start in any number of states. We gotta start in exactly one state because computers are deterministic. So I picked Q0 to be the start state here. Can Q1 be the start state possibly? Could I arbitrarily just say, set that arrow to point to Q1 instead? Could I do that? Would it change the behavior of the machine though? It might, but am I allowed to do it? That's the thing. I'm not getting an enthusiastic yes or no. Who votes yes? Could I do it? Who votes no that I can't do it? Okay, so it's mostly yes. All right. So I could set Q1 to be the start state, but I am setting Q0 to be the start state. And only in exactly one of these states will get this arrow thing. Okay, and then the final thing is, what does this double circle represent?
Acceptance state?
Yeah, so accept state. So remember from before we said all of the states in our machine could be set to 0 states or no states, or they could be 1 states or accept states. So the double circle here means accept or quotes yes. So if we end up in this state, then we say yes. Question for you. Because computers are deterministic, if I'm in Q1 and I still have input left, can I say yes right now? No, because computers have to do the exact same thing every time. If they see something on the input, they have to proceed because they're deterministic. Okay? So for that reason, if we've run out of input entirely and we're in Q1, can I now say yes? Yeah, because I've run out of input. So that's actually another thing that we're going to consider in our model. Let's just say that in your computer program, I provide you a string. Could you go back and forth across that string as much as you want if I give you a string of characters? Could I set a for loop to go forwards and then another for loop after it to go backwards? Could I do that? Yeah. So what we're going to do in our model is to make things a lot easier. You can only go forward in the input and never go backward. So what happens as a result is, because we can only move forward, if we've consumed a character, is that character essentially never going to be seen again? Yeah. So we're only going to move forward through the input. It makes the analysis a lot easier. Okay? We're trying to make this as easy as possible. Okay? So we're only moving forward through the input. So let's actually model what happens on a particular input, because it'll motivate the formal discussion later. So what is a possible input to this machine? Could I provide the input 111 to this machine? No, why not? Oh, there's no transitions anywhere in the machine labeled 1 out of a state or something. So what are the possible inputs for this machine from any state? 0. Here's another thing. Suppose that our inputs could be a 0 or a 1. Could Q0 have a 0 transition but not have a 1 transition? Because computers are deterministic? No. So in fact, every state in the entire machine must have all possible outputs that they could conceivably have. But could a state, for example, have, say, Q0, have 2 outputs labeled 0? Could a deterministic machine have something like that? No, because now it has to make a choice, right? I don't know which one I'm going to actually do. Could a machine have a 0 on one transition and a 1 on another? Yeah. But could it have no transition labeled 2, for example? Am I allowed to have that? If the input could have a 2 in it? No. What if the first character is a 2? What do I do? It doesn't know what to do. So I have to provide for every single state everything that could possibly happen. We'll have ways of saying, this is an unwanted input, do something with it. We'll have ways of dealing with that. But for now, we have to have every transition of every possible input present. Okay, so let's look at a particular input. So can someone give me an input, a valid input for this machine? 1010, is that a valid input for this machine? No, what is a valid input for this machine?
0.
0, 0. I'm actually going to put another one. It fits with my notes. Okay. So when I turn on the machine and I have not done any computation at all, I just turned on the machine. What state am I in? Q0. Why? Because that's the labeled start state. Good. So I'm going to model what state I currently am in. So I'm in Q0 right now. I have not read any input. Are we good? I know it's tedious, but it'll make everything else easy. All right. So now I'm in Q0, and I have read one character. There's only a 0 here to consider. But what state am I in after reading that one character?
Q1.
Q1, because I just follow the transition labeled with that character, and then after, I'm in Q1. Perfect. So now at this point, what state are we in? We're in Q1 right now. So do we have more input to read? Have we exhausted the input yet? No, we have not read all of the input yet. So what do? Help me along here. I keep going. So what do? What character do I read? The next 0. And what state do I end up in as a result?
Q0.
Q0 again. Cool. So we've exhausted that character. Are we done reading the input yet? No. So what do? We go back to Q1 after we consume the next character. Are we done exhausting the input yet? Yes, we are. So did we land in an accept state or did we not?
Yes.
We did. So what do I say on input 0, 0, 0? We say yes on this input. So we say accept. If I can write accept. If I fed you the string 0, 0, which has two zeros in it, what would you say on that input? No, or reject, or whatever your favorite word is. Here's another thing. Could I have said Q1's not an accept state, neither is Q0. Neither state is an accept state. Could I do that? No, I'm not asking whether it makes sense. Could I do it?
Yes.
Yeah, I could do it. It'd be a pretty dumb machine at that point. I'm wasting a state, but am I allowed to do it? Yeah. So I can have any subset of the states correspond to accept states. Okay? As long as it's a subset of the states, we're okay. Let's do a more complicated example. Or are there any questions about this example? Let's do a more complicated example with 4 states. And then 8 states, and then 16 states, and then you know what happens after that. So I'm going to have 4 states, zeros across on the top and on the bottom. And then 1s on the up and down between the 0 and 2, and then the 1 and 3 state. So I claim that this is a deterministic machine, where all the inputs could be a 0 or a 1 at any point. So this is something that unfortunately happens. A professor comes up and tells you something, and then you have to make the choice of whether you believe it or not. So this is something that is called proof by intimidation. So let me try not to intimidate you and not lead you down the garden path with this. So is this a deterministic machine?
Yes.
It's not me just telling you this. Is this, in your opinion or your observation, is this a deterministic machine?
Yes.
Yeah, why?
It has all the inputs and outputs.
Well, let's see. Let's look at every state. Does it have a 0 leaving it and a different transition labeled with 1? Well, look at Q0. It has a 0 going across, 1 going down, 1 same idea. 2, same idea. 3, same idea. Okay, so that's good. What if the inputs of this machine could be 0, 1, and 2? Is this a deterministic machine?
No.
No. So it's important to set at the very beginning what are the valid inputs to the machine. Because one set of inputs could be valid and then the other one might not be. So if the set of inputs that could be here is 0 and 1, we're okay. No problem there. So let's see. Can anyone give me a string that is accepted by this machine? Any string at all? Yeah, 0 is 1. What's another one? 0, 1, 0 is good. So let's just make a list of some accepted states. Strings. So 0 was accepted. 0, 1, 0 is also accepted. Just one, and we can make an infinitely long list, obviously. What about rejected strings?
0, 1.
0, 1's example. 1, 0. Let me write one for you. Ooh, what's that simple? Anyone happen to know? Epsilon. So yeah, so you're actually correct on that. It's actually the string with no characters. So let's look at the empty string here. So the empty string is the unique string without any characters in it. Okay? Well, is the empty string accepted by this machine? No. What state do we end up in after reading the empty string?
Q0.
Yeah, Q0. We don't go anywhere because we don't. Well, first off, there's no transition labeled epsilon here for reasons we'll get to. But more importantly, because the empty string has no length and going across a transition involves consuming a character, empty string has no characters, so we can't execute a transition. So therefore we are stuck in Q0 and therefore we are not accepted. Cool. Let's go back to this machine for a second. The 0, 0 machine up above. Can anyone give me an English description for what strings are accepted by that machine?
Odd number.
Yeah, odd number of zeros. Anyone disagree? Yeah, and we can actually prove by induction that it is. Well, the string of length 1 goes there, and every odd length above a certain number is because we can just do however many transitions we need to do, and then one more back, one more forward. And then the even length strings are not because we always end up at Q0. In fact, the name Q0 represents the modulo by 2, so the parity of the length of the string. So if we take a string of length 100 and modulo 2 that, what is 100 remainder 2? 0. And so therefore we end up at Q0. So the name actually is kind of helpful here. By the way, you may be wondering why states are named Q whatever. That's actually just purely tradition. I have no idea why they're called Qs, whatever. In fact, a better name would have been S something for states, but Q is just the name that was picked. What about the second machine? Anyone happen to know what that is? Yeah.
Odd number of zeros or odd number of ones?
Odd number of zeros or odd number of ones. I'll disprove that. Pick any string with an odd number of zeros and an odd number of ones. That has even length.
0.
Yeah, 0, 1, for example. And then we'll end up in Q3 as a result.
Sum of 0
So that's one formulation. So the number of zeros plus the number of ones is an odd number. That's another way to look at it. Yeah.
Odd number of zeros or odd number of ones, but not one.
Yeah, so that's another formulation. Here's a much easier formulation. Odd length strings. But what is the difference between these two machines? What does the first one have that the second one has that the first one doesn't? It has ones on the transitions. So could we actually make this second machine simpler than the one that's here with 4 states? In fact, we can. So we can do something like this. And then that works. It's exactly the same set of strings. These two machines accept the same strings because they do the same thing. So you may be wondering, okay, Ryan, what is this comma right here? So this comma represents multiple transitions. So it's not the transition labeled 0, 1. It represents a transition labeled 0 and another transition also labeled that's labeled 1. And then the same idea in the back direction too. So these are 2 examples of this deterministic machine. Any questions on these? Cool. Is this formal? This picture right here, is that formal? So this Q0, Q1 one, or this 4-state one, or this 2-state one down here, could I present this to a computer and say, compute it on this string? Could I present that picture to that computer? What does it need? It needs a specification to say, here are the exact state names. Here are the characters that are allowed on the input. Here are the transitions. Here's the start state. Here are the final states, provided as lists or whatever. But it's provided in a formal way to the computer. And then the computer, upon receiving those 5 bits of information, goes, now I know what deterministic machine you're talking about. Okay? So do you think there's a reason why we should care about formalisms? Maybe you don't, but we'll get there. All right. So, but mainly the reason is that you could be talking about, so in fact, the interaction that we just had where a student just said an odd number of zeros or an odd number of ones. But I gave a counterexample. But the student probably thought an odd number of zeros exclusive or a number of ones. Is that the case? Say yes. Okay. Yeah. So there's a problem here. English is extremely informal. So I could be saying something to you, and then hopefully you understand, but there could be some miscommunication here because you grew up in a different background than I may have. I may say things in a way that you might not understand. English is a terrible way of communicating formalisms. So we need a formal specification that is unambiguous here. So what do we want? We want a machine that's deterministic and has those 5 parts that I mentioned before.